Welcome to my tutoring session in chemistry. The current video is part 2 of the 7-part series in HPLC. In this video, I'll explain the general features of instrumentation in HPLC with schematic workflow of a typical HPLC setup. Here's a figure depicting the schematic workflow of a typical HPLC setup. We have a solvent reservoir, and the solvent reservoir is filled with the solvent system used for the separation process. Now, before filling the solvent reservoir with the solvent system, the solvent or the mobile phase has to be filtered using a 0.45 or 0.2 micron membrane filter under vacuum. And this is done in order to remove any particulate matter or impurities present in the solvent. And this will be followed by ultrasonication, which removes any air bubbles present in the solvent. So first, filter the solvent using membrane filters, and this will be followed by ultrasonication. Membrane filtration removes the particulate matter or impurities, while ultrasonication removes the air bubbles. Now, the solvents used for HPLC, it should be of analytical grade or HPLC grade. Now, HPLC grade solvents are commercially available. Some of the commercially available polar solvents are water, methanol, and acetonitrile. A degasser, it removes dissolved gases like oxygen and nitrogen present in the solvent, and this is accomplished by purging or passing the helium gas through the solvent. By doing so, dissolved gas like oxygen and nitrogen are displaced or removed from the solvent system. A high pressure pump, it delivers the solvent from the reservoir onto the HPLC column. A pulse dampener is located between the high pressure pump and the analytical column. The function or role of a pulse dampener is to dampen the pressure fluctuations generated by the high pressure pump. So basically, the pulse dampener, it smoothens the pressure fluctuations and makes sure that the solvent or the mobile phase, it travels through the or flows through the column at a precise and controlled flow rate. So the mobile phase, it flows through the column at a constant flow rate, and this is aided by the pulse dampener. Now, first, the mobile phase, it flows through the pre-column. Now, it is called pre-column because the mobile phase, it enters this column before entering the analytical column where the actual separation takes place. Hence the name pre-column, as the mobile phase enters this column first. It is also called as guard column, as it protects the analytical column from particulate matter or impurities. It is also called as pre-filter, as it removes or filters out any particulate matter or impurities present in the mobile phase. Now, no separation takes place in the pre-column. The actual separation takes place in the analytical column. And the packing material present in the pre-column is same as that of the analytical column. So the packing material is same both for the pre-column as well as the analytical column. Only difference is that in the pre-column, the packing material is less, while in case of analytical column, packing material is more. So packing material here, I am referring to the stationary phase that is used for the separation that is present in the HPLC column. Now, the function or role of a detector is to monitor the elution process. It monitors the eluent that is coming out of the column, and it detects any components which elutes the column. Now, generally, without the sample mixture flowing through the column, the radiation or the UV radiation that is given by the UV lamp, it passes through the solvent system that is coming out of the column, and this is detected by the detector. So the radiation that falls on the detector, it has to pass through the solvent or the mobile phase that is coming out of the column. So under these conditions, as there are no samples coming out of the column, you get a baseline in the chromatogram. Now let us inject the sample mixture into the column, and this is done via a multiport valve. So let us say we are injecting the sample mixture consisting of components A, B and C highlighted in red, blue and green. Now the components, they travel at different speeds along with the mobile phase. And the speed at which they travel depends on their relative affinity towards the stationary phase. The components with greater affinity towards the stationary phase travel slower and is retained for a longer period of time. While the components with lesser affinity, it travels at a faster rate and it comes out of the column first, or it is eluted at a faster rate. Now here in this case, we can see that the red component, it is coming out of the column first, as it is having a weaker affinity towards the stationary phase. So it is more soluble in the mobile phase. And once it crosses the path between the UV lamp and the detector, it absorbs the UV radiation. The moment the molecule passes the path and when it absorbs the UV radiation, the detector, it immediately detects the absorption of the radiation by the sample. It generates an electrical signal which is amplified and recorded as a signal, which is seen as a chromatogram. Now chromatogram is a plot of retention time on x-axis against the concentration or absorbance on the y-axis. Now for the current separation, we are making use of a C18 column, which is a non-polar stationary phase. Now C18 column, it is constituted by silica bonded octadecyl group, which is shown as in the form of strands, which is adhering to the inner walls of the column. So the strands adhering to the inner wall of the column, they refer to the non-polar aliphatic chain. So it is a 18 carbon chain and therefore it is non-polar in nature. And this is an enlarged diagram of the analytical column where the actual separation taking place. So the column is packed with a non-polar stationary phase shown as strands through which the polar mobile phase is flowing through. Now for the current experimentation, for the separation of the mixture ABC, we are making use of polar solvent mixture comprising of water, methanol and acetonitrile. Now along with the flow of this polar mobile phase, when the sample is injected, the components, they travel at different speeds during the separation in the analytical column or the HPLC column. Now the speed at which these components travel in the column along with the mobile phase during separation depends on the relative affinity towards the stationary phase. So the component with greater affinity towards the stationary phase, that is the green molecule, it is retained for a longer time as it is a non-polar molecule. So the rule of thumb says that like dissolves like. So there is attraction between like molecules. So non-polar molecule is attracted towards non-polar stationary phase, and therefore it is retained for a longer time in the column and hence it is eluted last. It comes out of the column last. While the polar molecule, which is having weaker affinity or attraction towards the stationary phase, it travels at a faster rate and it comes out of the column first. And the molecule of intermediate polarity lies between these two. So the component which is coming out of the column will be detected first by the detector, and immediately you will see a peak. And you can see three peaks: a red peak, blue peak and a green peak for these three respective components that is being separated during the process. Now HPLC is a powerful analytical technique which is used for analysis of non-volatile and heat sensitive compounds, which is called as thermally labile. Now this technique is named as high pressure liquid chromatography or high performance liquid chromatography. It is named as high performance liquid chromatography because of its superior or better performance as compared to the conventional column chromatography, and also because of high resolution power as compared to the conventional column chromatography. And it is called high pressure liquid chromatography because the mobile phase, it flows through the column at a high pressure. And why high pressure has to be maintained in the column, or what makes the need of high pressure? The reason is the particle size of the stationary phase is very small. It is around 1 to 5 micron meters. The column is very narrow and the column is tightly packed with the stationary phase. So small particle size, narrow column and tight packing of the stationary phase. All these three factors, they offer a greater resistance to the flow of the mobile phase. And hence the operating pressure of the HPLC is usually high. It is generally around 1000 to 5000 psi. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.